In this example, we're going to look at how to use Green's theorem to make short work of line integrals over closed paths. So here we've got the vector field f of x and y equal to f naught over L, which are both constants, times 0x. And we're asked to evaluate the work that this vector field does on some particle that goes around the path C, which is an L by L square path, which we can imagine starts at the origin if we want. Now previously, if we wanted to do this type of calculation, there'd be a lot of work and setup involved. We'd start off, for example, by saying, let's define each piece of this path to be some segment, C1 through C4, and then we'd come up with parameterizations for each segment, and do basically 4 line integrals and add together all the results. This would be a lot of work. For this particular vector field, we could try and be clever and reduce the amount of work by making certain observations. Like, for example, we could argue that our force is parallel to the y direction, and so for the paths C1 and C3, which are only in the x direction, the dot product between the force and the velocity is going to be 0, so there's going to be no work there. Okay. So work 1 and work 3 are going to be equal to 0. We could also argue that along C4, my force is just going to be equal to the 0 vector, and so that gives me that the work along that path is going to be 0. But we're still left to calculate the work along the path C2. And so that means parameterizing C2, which we could do quickly here and say this is equal to L and T, and it runs from 0 to L. Then we find our velocity, which is just 0, 1, and we evaluate our force along that leg. And that's going to be equal to, we just plug L for x into this, and we get F naught over L, 0 L, so that's just F naught, 0, 1. When we take the dot product of those, we'll just get 0, 1 dotted with 0, 1 times F naught, which just gives us F naught. And then we can integrate this to get the work along that second leg. It's the integral from t equals 0 to L of this dot product, which is just equal to F naught times dt, and that works out to F naught L. The total work is equal to the sum of the work along each leg, but I argued that the work along the other 3 legs was equal to 0, so this would give me that the total work is equal to just the work along this leg, and that's F naught L. So that's how you could solve this problem calculating the line integral directly. I used just about every trick I know to simplify the amount of work involved, but it was still a non-trivial problem. Now, what I'd like to show you is how could we solve this problem using Green's theorem? Well, since I have a closed path, Green's theorem tells me that the line integral around that closed curve, oriented counterclockwise, which it is here, is going to be equal to the double integral over the region D, which is enclosed by the curve, so this region up here, this square, of the partial derivative of my y component of the force field with respect to x, minus the partial derivative of the x component of my force field with respect to y, integrated over that area. But remember what the vector field was. It was f of x and y equal to F naught over L, 0x. This means my F1 component is 0, and the F2 component is F naught x over L. So when I compute the partial derivative of F2 with respect to x, I'm just going to get F naught over L. And F1 is just 0, so that's just going to give me 0. So this is equal to the double integral over that square region of F naught over L dA. But F naught and L are just constants, so I can take those out of the integral, leaving me with just an integral of dA over the region D. But this thing, with no argument in this integral, this is just the area of that region. And that's equal to the area of the square, which is just L squared. So this whole thing is just equal to F naught over L times L squared, or F naught L. This is the exact same result that we got up here for the work. But compare how much effort went into this calculation versus doing the line integrals directly. Green's theorem provided us with this amazing shortcut by relating the integral around the closed curve enclosing the region to a double integral over the region itself. Alright, that's all I wanted to say for this example on Green's theorem. Thanks a lot.